Hi everyone, this is Mr. Hall and this is a really quick video about Le Chatelier's principle with equilibrium and temperature. Hopefully you've come in with a bit of understanding around how Le Chatelier's principle works in general, in particular with concentration. With temperature it's actually really similar. It all depends on how you consider heat to be when you're dealing with chemical equations, and it also basically requires you to understand the difference between an exothermic and an endothermic reaction, which you should know from when you did energetics in prior studies. Okay, so hopefully you've done that before coming to this point. So in today's video, there are two things which I'd like to go through. The first one is to deduce the correct shift in equilibrium if there is a change in temperature, i.e. working out whether the equilibrium will shift to the left or to the right, whether you heat up or cool down a reaction. And then the second thing is to explain that shift in equilibrium if there is a change in temperature by reference to the equations energetics. Okay, so first off, the first thing I just want to emphasize, and it's something which I've emphasized before and I want to hammer home again, is with Le Chatelier's principle. It's quite wordy if you look it up in like a chemical textbook or a website, but the key idea really is the system will always try to oppose the change. So whatever you do to it, heat it up, cool it down, increase the concentration, decrease the concentration, increase pressure, whatever, it doesn't matter. The system will always try to oppose that change to re-establish equilibrium. I think earlier on I talked about how if you've got someone running up a escalator and the escalator's moving down but they're moving up, if the escalator moves quicker down, then that person, in order to kind of stay on the escalator, they're going to have to run faster in order to kind of stay in the same position. They might initially move down a little bit, but they're going to have to run quicker just to kind of keep pace and stay in the same place. And the same is true of equilibrium as well. It's dynamic. So let's have a look at a couple of examples in terms of equations. So here I've got an equation that comes up quite a lot. It's a cobalt complex, and on this complex, you're going to either have water attached to it, which is this H2O thing over here, and that solution is pink. And if it's in solution with chloride ions, that's an equilibrium to form this kind of cobalt chloride complex, which is blue, and then that eliminates 6 lots of H2O. Okay, so you've got the pink solution and the blue solution. It's quite a good experiment you can do in the lab. Not very good for a video because you have to wait for several minutes, and even then, instead of turning blue, it sounds like a deep purple. It's okay, but it's not perfect. Anyway. So, now the reaction above is endothermic. Okay, now if it's endothermic, what that means is that the reaction needs heat energy in order to get started. Okay, if you want to be really fancy, you could draw like a reaction profile. So we look a little bit like this. So here's your reactant, here's your product. It needs to take in energy, so it's going to look a little bit like that. Okay, in order to get going in terms of reaction profile. Now, because it needs to take heat energy in to get started, you can consider heat energy to be a reactant. Now, I know that heat energy is not a thing as such, like a substance, but we can include it as something actually on the equation itself, and this is really useful when you're trying to think through problems. As a result, I'm going to consider heat to be a reactant for my endothermic reaction, and I can write it on the equation like so. So when you're doing any problem with heat and Le Chatelier's principle, always write heat as either reactant or product, depending on what the reaction is. Here it's endothermic, heat's been taken in, so I write heat as a reactant like so. Okay, now there's two things that you can either do to reaction mixture. You can either heat it up or you can cool it down. Let's look at each one in turn. So first of all, let's say that I increase the temperature. Okay, so here's my reaction. I'm going to increase the temperature. Now if I increase the temperature, it means I'm adding heat. Now that basically means I'm adding reactants. I'm just going to draw an arrow here just to represent the fact that that is the first stress that I'm putting on the system. Now if you remember, if I'm adding something to a system, it means I've got an excess of that particular thing. So by having extra heat in this reaction, I have an excess of reactant. Now, if you remember what I mentioned a few minutes ago, the system wants to oppose the change. So to oppose the change, it will want to do that by reducing the amount of reactant to re-establish equilibrium. And that's all because this reaction is endothermic. So in order to make this work, it has to increase more of this, and I'll draw that as an arrow above it. Therefore, if I'm making more product in order to re-establish equilibrium, it means my equilibrium is going to shift to the right. Now, it's crucial wording here. Instead of trying to say that where have I gone? Instead of trying to say that the reaction shifts to the right, you have to say the equilibrium shifts to the right. So if you can see the blue triangle is going to shift to the right-hand side, so my equilibrium shifted that way. Equilibrium being re-established, the rate of the forward and reverse reactions will eventually be the same. However, the concentrations might be different. So I might have a greater concentration of the blue cobalt chloride complex and a smaller concentration of the cobalt sort of water complex, for want of a better word, but the rate of making both of those will be the same. Okay, it's just shifted to the right. So that's if I increase temperature. Now, if I decrease temperature, the opposite will happen, okay? So if I'm decreasing, that means I'm going to remove heat, which means I'm basically reducing the amount of reactant available, okay? That means I've got an excess of product, okay? Now, in order to counteract that, what the reaction will want to do is oppose the change. To oppose the change, it's going to have to make more reactant, okay? So the response, I'm just going to draw it up here, is to have more of this. Now, if it wants to make more of that, it has to use up some of the product to make that reactant. Therefore, my equilibrium is going to shift to the left-hand side, okay? That means I'll get a greater yield of reactant, a lower yield of product, so my solution is going to look a bit pink, okay? And that's basically how it works for endothermic reactions. Now, exothermic, it's the same idea, but we just kind of have to reverse our thinking because of the nature of the reaction. Now, this reaction, as I said before, is exothermic. If it's exothermic, it's releasing energy. Therefore, if I draw a reaction profile for this, it will look a little bit like this. So I start off with ICL and Cl2, which will be here high in energy. Because it's exothermic, it drops in energy because that excess energy gets released as heat. So it releases heat energy, therefore I can consider heat to be a product. Okay, so I can write that on my equation like so. Now, because heat is a product in this particular reaction, it means that I have to deal with things slightly differently when I'm talking about whether I increase the temperature of that reaction mixture or whether I decrease the temperature of that reaction mixture. Now, let's say I increase the heat. Now, if I increase the heat of this reaction, that means that I've got an excess of product, okay, which is over on the right-hand side, like so. Now, if I've increased the heat of this reaction, as I said before, the system will always want to oppose the change. The only way it can oppose the change here is by reducing the amount of product, and it will do that by making more reactant, okay? And that will be over here. I'll do it as a double arrow just to show that's the second step. Now, if it's making more reactant, it means my equilibrium has shifted to the left-hand side, like so. Therefore, I'm going to have a lot more of ICL and Cl2, and I'll have a bit less of ICL3 because the equilibrium shifted to the left. The rates will re-establish, and they'll be the same. I'll just have different concentrations of reactants and products on both sides. So that's all fine and well. That's basically the nuts and bolts of how it works. How do we actually apply this in practice? So this is a typical question you might get. It's actually a bit more wordy with a bit more detail than you might actually get. So it says here, consider the following equation. H2 plus F2 makes 2Hi. This is yellow, this is colourless. If the temperature is increased, predict the change in position of equilibrium, an explanation for the shift with some stuff on it, the change in yield and the change in colour. Now, to be honest, you're probably not going to get all of this chat in an exam style question. It'll be very, very scaffolded if you do. What they'll probably just say is describe what will happen to the reaction, or describe the change in product or reactant if I increase the temperature or decrease the temperature. Okay, so when you're answering these questions, following this kind of scaffold is very, very useful. And I'll explain how you're going to do it. So first thing we need to mention is that the temperature is increased. We also notice that the reaction is exothermic. Now, if the reaction is exothermic, it means it's releasing heat. So the first thing I do is I write that on my equation. Now, remember, you're only going to have one or two of these to do in the exam. So you might as well go to town and get it done to the fullest of your ability. So it's going to be plus heat. I'll write that in. Okay, now that's done. Now, that's the first bit. Now, this is saying if I increase the temperature. So if I increase the temperature, I'm increasing this, which is an increase of reactant. The system will want to respond by opposing the change. Therefore, it's going to increase the amount of reactant. Therefore, my equilibrium overall is going to shift to the right. Now, that's the basic stuff. The key and probably the trickier part is actually putting this in wording. So the first bit I need to do is mention the change in equilibrium. Okay, so the first thing I have to say is the equilibrium shifts to the left. Okay, that will give you 1 mark in most exam situations. Now I have to explain it. So what's the stress on the system? Now, the thing I haven't mentioned here is you have to mention the nature of the reaction. So the first thing you have to say is the reaction is exothermic. Okay. Now, you may have noticed I've written the reaction as exothermic here already. To be honest, in most reactions, they may not even give you that information. Instead of saying exothermic, they might say the reaction releases heat. And then from the fact that the reaction releases heat energy, you should be able to deduce that the reaction is exothermic. So sometimes you have to work that step out, so just be aware. So the reaction is exothermic. The next thing I have to say is the stress on the system. I've done this bit already. So the next thing is the stress on the system. The stress on the system is this increase in temperature. So I say that the temperature has increased. And then you have to say what the response from the system is. So you'll say the system responds by opposing the change. Now this is your stock line. Whether you're dealing with pressure, concentration, temperature, it doesn't matter. You always say the system wants to oppose the change. And then you can finish off with it does this by reducing the temperature, okay? I'll just put temp there, and it'll do that obviously by shifting to the left. Now to finish off, I can tick these off, that's done, that's done. I now need to talk about the change in yield and the change in colour. So I'll combine C and D as one sentence, just because I'm running out of room. So I can say the yield. Now, because you're shifting to the left-hand side, your concentration of reactant is going to go up, as I've noted here. All right, that's going up. Therefore, in my sentence here, I'll say the yield of reactant increases. Sorry for the slightly untidy writing. And that's straightforward. Yield of reactant increases. And then the colour, sometimes you have to mention it. It depends if they give you the information. In this case, because it shifted left, my gaseous mixture in this case will turn yellow. So I'll write, so colour is yellow. Oh, there we go. And that's everything done. So that for me is sort of like the most complete answer as you can have in terms of using Le Chatelier to explain more complex problems. These are typically in things between 2 to 4 marks. It kind of depends on how the exam board feels on the day when they set these questions out. But the more complete your questions are, the better chance you have of actually getting that right. And that's it. So I hope this has been useful, and best of luck with your Le Chatelier problems. Next up, we'll talk about Le Chatelier and pressure.